Good evening, everyone. So today in this video, we are going to discuss the chapter magnetism, magnetic effects of electric current, which is very essential for class 10. So we will discuss this chapter in one single video. So see the whole video for better knowledge of this chapter. So first we will learn what do you mean by magnetic effects of electric current. Suppose this is a circuit. Circuit. If switch is on, then obviously electric current will pass through the circuit. In that case, if electric current passes through the circuit, the bulb will glow. In that case, around this circuit, around the conductors, a magnetic field is produced. In this region, around the conductor, around the electric field or electric circuit, a magnetic field is produced, which is termed as magnetic effects of electric current, and simply it is known as magnetism. Okay. So first, this effect, when electricity passes through conductor, magnetic field arises. This effect was discovered by the scientist Ørsted, Hans Christian Ørsted. Now, what is magnetic field? So, simply this is a conductor. Say, any current, I amount of current is passing through the conductor. In that case, I have already told that a magnetic field is produced around the conductor. Okay, now, here some magnetic lines are there. Magnetic lines, the same as the electric field lines, magnetic field lines are there. So the intensity of the magnetic field, which implies the force of the magnet, that is magnetic field. So due to the arise of this force, the magnetic field or magnetic effect arises. So in this chapter, we will check first about the bar magnet. How magnetic field lines produces in a bar magnet? So simply, this is a bar magnet. So you have know that a bar magnet has two poles. One pole is called north, another pole is called south. So if any compass means say by which you can see the direction. So this is the arrow which is inside the compass. This arrow indicates north and opposite to this is south. So if any compass is kept here in this region, then the arrow will direct it like this. Or same condition, if you keep a compass in this region, then the direction will be like this. So here again, if you keep another compass, it will show this type of direction like this. Now, if you join the all points, then you will find a continuous line, and this line states the magnetic field lines. Okay. So in case of bar magnet, you can draw the magnetic field lines. So this is north, this is south. Here the magnetic field lines arises from north, ends at south. Same thing. This will be a direction. Here also, the radius of the circle or the circular part may be very large. That's why you can join a circle also. But only by using compass you can find out the directions. In which direction the field lines travels. Okay. At the center of the bar magnet, it will be straight line. Straight line means what? It is infinite. You can take as an infinite circle. It will produce a circle, but somewhere at infinity. Okay. Now see in my diagram here in this region, the strength, the magnetic lines are close to each other. Here also and this region also. Magnetic field lines are close to each other. But in other regions, they are in between the lines, there is a gap. Okay? In the other region, in between the lines, all the lines, there is a gap. But at the poles, there is no gap, very small gaps in between the lines. So from this activity, you can come to a conclusion that magnetic field lines are always arises from the north pole, okay, and ends at south pole. And these lines are continuous. I have already told. It means that the lines will again join to the north pole. So inside the bar magnet, the magnetic field lines are parallel to each other, or you can say they are straight parallel lines. And direction of magnetic field outside the bar magnet, it is from north pole to south pole. Arises from north and ends at south. And inside the bar magnet, the direction is from south to north. Okay. Now these are the two properties. First property is that it always arises from north and ends at south. Outside the bar magnet, magnetic field line directed from north to south. Inside the bar magnet, from south to north. It means that they are continuous closed curve. And third point is, say this is one magnetic lines, this is another. Here, say if possible, they intersect here. But this is not possible in case of magnetic field lines. Why? Magnetic field lines always show a direction from north to south. Okay, that means only one direction. So if you take one compass here, then according to the lines, the compass neither need to show two direction. One is like this, another one is like this. But for only one compass, it is not possible. That's why two magnetic field lines never intersect each other, which is a very important property of the bar magnet. That means magnetic field lines of a bar magnet. And question may come like, why two magnetic field lines does not intersect each other? So 2 marks. Then you have to write, say at that point, intersecting point, the magnetic compass needle must show two directions for two different lines. But we know that magnetic field lines have only one direction. So at that point, the compass needle must have to show two directions, which is not possible. It means that magnetic field lines never intersect each other. Okay? This is about the bar magnet. Next, we will see direction of magnetic field lines in a straight conductor. Straight conductor. Okay. Suppose this is the conductor. Okay. Now, this rule, direction of magnetic field lines in a straight conductor, this rule was stated by Maxwell, which is also known as Maxwell's right hand thumb rule. Maxwell's right hand thumb rule. Suppose this is the straight conductor. Now, hold the wire like this. So your thumb points to the direction of the current. So this is the direction of current. Now your other fingers, this will be the direction of the magnetic field. So suppose this is the straight conductor, direction of current. Now the direction of the magnetic field lines will be like this. This is the other four fingers will direct the magnetic field lines. This one. Say direction of current from upward to downward. In that case, you have to hold the wire like this. Then this will be the direction of the magnetic field. This is the direction of magnetic field according to the Maxwell's right hand thumb rule. Okay, you need to memorize this. For magnetic field line, direction of magnetic field line in a straight conductor. Okay. Now, say from Maxwell's right hand thumb rule, if the current directed from downward to upward, this will be the direction. From upward to downward, this will be the direction. Okay. Now, this magnetic field is directly proportional to the amount of current applied. So suppose here you are connecting a battery. So here battery is connected. Now 5 ampere current is applied. Now if you increase the amount of current, say suppose another 2 ampere, that means total 7 ampere current is applied. In that case, the strength of the magnetic field will be more. That means magnetic field is directly proportional with the amount of current flowing through the circuit or the straight conductor. Next, it will inversely proportional to the distance of the point from the conductor. Suppose here is a point. One question is there is a point P, there is a point Q. So suppose I ask you a question. In which point the strength of the magnetic field will be more? Here the point P, distance of point P is less as compared to the distance of point Q from the conductor. Distance is perpendicular distance. From this activity, you can come to a conclusion that the magnetic field at P is more stronger as compared to Q. It means that it is inversely proportional. The magnetic field is inversely proportional with the distance of the point from the conductor. If the distance increases, magnetic field decreases. If the distance decreases, magnetic field increases. Clear? So this is the direction of magnetic field lines in a straight conductor. Now we will apply this rule in case of circular current carrying loop and in case of solenoid. Now this is a circuit. Suppose one straight conductor and the conductor is connected to a battery. Okay, that conductor is passes through a rectangular sheet. Okay, now if you consider this point of the conductor, if you consider this point, then you will observe a pattern of concentric circles. Okay, at every point of a conductor, if this is a straight conductor, at this point the magnetic field lines will behave like a set of concentric circles. At this point, a set of concentric circles. That means at every point of the conductor, magnetic field lines will be a set of different set of concentric circles. Clear? Now, what will be the direction of the magnetic field? Suppose current is flowing from downward to upward. So in that case, say this is the conductor. If you hold the conductor like this, then your other four fingers will direct the magnetic field. So in that case, it is like that. So direction of magnetic field will be this. If you increase the amount of current here, then you will see this type of concentric circles. If you decrease the amount of current here, then there is you will able to see there is a gap in between the concentric circles. Clear? Now next we will apply this rule in case of a circular conductor. So this is a circular loop. Circular loop, and this loop is connected to a battery. So this is plus, this is minus. This is connected to a battery. Now current is flowing through the conductor in this direction. This will be the direction. Clear? Now, if you consider this point here, if you consider the conductor as a straight conductor, then hold the conductor like this. Now your other four fingers will direct the magnetic field. Here, a set of concentric circles. So if you hold the conductor like this, then your other four fingers will direct the magnetic field. So if you like this, so direction will be. If you consider any point here also a set of concentric circles. Here, direction of current is like this. So hold the conductor in this direction. Then your other four fingers will show the direction. As per your other four fingers, as per the Maxwell's right hand thumb rule, this will be the direction of current. So according to this, here circular lines, these are the magnetic field lines. This will be a direction, this will be a direction. In the center, through the center of the circular loop, it will be like straight line. Now, If you consider the whole circular loop, in that case, this side will termed as south and this side will termed as north. Why? Because see the direction of magnetic field. In case of bar magnet, we have already studied that direction of magnetic field lines is from north pole to the south pole. So it arises from north, ends at south. Arises from north, ends at south. So these are the direction of magnetic field, and by using Maxwell's right-hand thumb rule, you can find the direction of the magnetic field lines in a circular current carrying loop. So here two conditions you can write that here also magnetic field, the strength of magnetic field will directly proportional to the amount of current. If the amount of current increases, then the strength of the magnetic field also increases. Okay, and it will also the inversely proportional with the radius of the circular loop. In case of this circular loop, the magnetic strength of the magnetic field will be more as compared to this circle because radius of this circular loop is less as compared to this one. Clear? These are the two conditions you can write. Next we will see in case of a solenoid. Now first condition is what is a solenoid? A solenoid is also a loop. So you can also prepare the solenoid. You can take a copper wire. Remember, you have to take insulated copper wire. So copper wire and design the copper wire like this. And then connect it to a battery. Now see the direction of current. This is plus minus. So direction of current. These are the direction of current. Okay. Now by using the same rule, Maxwell's right-hand thumb rule, see what will be the direction of the magnetic field in case of solenoid. First, it is right-hand thumb rule. So hold the conductor here. Then it will behave like this. It means that here also these are the direction. So if you draw the magnetic field lines, direction is like this. So it will come here also. Direction of current is, these are the direction of current. If you hold the conductor here, then also this direction. These are the direction. So here infinite number of circles will be there, circular path will be there. This path will be the direction of the magnetic field. So here the magnetic field arises from this side. These are the direction of the magnetic field and ends at this pole. So now we can consider this pole will be north pole. This will be south pole. So the solenoid will also behave like a magnetic field. So if a question in a question, the question is like that. So state two methods by which you can prepare a magnetic field. Okay, you can prepare a set of magnetic fields. So you can write about the solenoid, you can write about the bar magnet, you can write about the circular current carrying loop. So this will be north, this will be south. And same at the center of the solenoid also, it will be a straight line. Straight line means infinite circle, radius of infinite radius circle. Clear? So this is a solenoid. Now where you will use apply this rule, solenoid. You know electromagnetic induction. So this is the conductor. Okay, conductor. Now if you wrap an insulated wire like this, and the two terminals will connect to a battery. You can add one switch also for precaution. Now, if you connect a conductor like this, you can wrap the wire throughout the conductor. Then the whole conductor will behave like a magnet. and this is called electromagnet, which is very important. You can use this as a magnet. So when the switch is on, it will behave like a magnet. But remember, this is not a permanent magnet. Okay, permanent magnet means you can say about a bar magnet. These are the permanent magnets. Bar magnets, horseshoe, horseshoe magnets, round, that means circular magnets. Bar magnet is like this, north and south pole. Horseshoe magnet, like these are the horseshoe magnet. One pole is north, another pole is south. So these are the permanent magnet. But this magnet is not permanent. So when you on the switch, the conductor will behave like magnet. When you off the switch, the conductor will behave like a normal conductor. Clear? So these are the applications of the right hand thumb rule, Maxwell's right hand thumb rule in different areas like circular loop, like solenoid. By using solenoid, you can prepare an electromagnet. So next, we have discussed about the magnetic field, direction of the magnetic field. Now, we will see the force which may arise in a magnetic field. Suppose this is a conductor, okay? Conductor, which is the two terminals is connected to a battery. Okay. Now the conductor is placed in between a horseshoe magnet. Okay, conductor is placed. You can connect the wire like this. Conductor is placed. This is north, this is south. In between two, a horseshoe magnet. In between the poles. Now, when you on the switch, suppose there is a switch. When you on the switch, you will see a deflection of the conductor. Say this AB is the conductor. AB is the conductor. When you on the switch, it will show some deflection. Why? Because there is a magnetic field produced due to the presence of this horseshoe magnet. So from this activity, you can write you can come to a conclusion that when magnetic field produces the electric field, that means electricity, it can produce the magnetic field, and due to the presence of the magnetic field, the conductor may displace. It means that there is a force, and that force arises due to the presence of the magnetic field. Now, what will be the direction of this force? This direction was stated by a scientist that is named Fleming, which is known as Fleming's left hand rule. So what is Fleming's left hand rule? Now suppose your first three finger, see, your first three finger of the left hand, you can place your first three finger like this. All the three fingers, see, these two fingers are perpendicular to each other. Now hold your middle finger also in a perpendicular direction. Now all the three fingers are perpendicular to each other. If your middle finger show the direction of current, okay, if your middle finger show the direction of current, and if your forefinger show the direction of the magnetic field, then your thumb will show or direct towards the force of the magnetic field. Okay? I repeat again. If your middle finger show the direction of the current, if your forefinger show the direction of the magnetic field, then your thumb will show the direction of the force. This will be the direction. Okay, you can hold like this. So this is current. Current. Middle finger. So this is magnetic field. Forefinger. So this is force. This is thumb. And this rule is applicable for any kind of magnetic field. by which you can find out the direction of current, direction of magnetic field, as well as the direction of force. Now let's see some activities. Suppose this is the direction of magnetic field. In this plan, this is the plan. Suppose consider this is the plan. This is the direction of magnetic field. Now, say this is the direction of current, which is perpendicular. Okay, perpendicular to the magnetic field. Now tell me what will be the direction of the force applied on the magnetic field. Now you have to hold your three fingers. Say magnetic field. This will show the magnetic field. Okay, current. This is the direction of current. Now see the direction of your thumb. Direction of your thumb is onto the base, out of the base. If this is a base, if you consider this is a plan, then your thumb will guide it out of the base. If the direction of current is like this, then see, this will be the direction, magnetic field, current. Now this thumb, it will guide it into the base or into the plane. Now always remember, always magnetic field and current, these two directions are always two dimensional. When you have to find out the direction of force, then the direction will be, if you consider about your right, left, north, south direction, then the direction of the force will be upward or downward. Or if you consider like this plan, then the direction will be, it may be out of the base or into the base. These are the two directions of the force. Clear? Now suppose you are standing in a medical, okay? Behind you there is an X-ray room. So some alpha particles are scattering from that room. The direction of the alpha particle is from your back to your front. You can take the direction of alpha particle direction as current, from your back to your front. Now due to the presence of the magnetic field, direction of alpha particle what? Is like this, direction of current, from back to front. Now due to the magnetic field, presence of magnetic field, these alpha particles displace towards your right. Displace towards your right. That displacement means, remember always, this will be the direction of force. This is the direction of alpha particle, it displaces towards your right. Now this is force towards your right. This is right, this is the direction of alpha particle, that means you can take as a direction of current. This is the direction of force. What will be the direction of magnetic field? See, direction is upward. Clear? Now in the same alpha particle deflects towards your left, then direction of the magnetic field to the downward. So these are the direction, you can find out the direction of current as well as direction of magnetic field as well as direction of force of the magnetic field. Now last topic we will discuss about the household circuit. Household circuit. Connections of electricity. Okay, electric wires connection. How you will connect the electric wires in your home. Okay, first thing, from the transformer. Okay, from the transformer, that means from your post. Okay, current post. Two wires are connected. Two wires are connected. The red insulated wire you can name as live wire, and the black insulated wire you can name as neutral. Clear? The potential in our India, the standard potential of the live wire is 220 volt, and the potential of the neutral wire is 0 volt. Now what will be the potential difference between these two? 220 minus 0, the potential difference here, it will be 220 volt. Clear? Now first these two wires will enter into fuse. This is a fuse. Clear? Enter into fuse. This is a block diagram. For better diagram, you can take the reference of your NCERT diagram. Clear? The neutral wire also will connect to the fuse. Here inside the fuse, the live wire is connected to the fuse wire. Okay? And then both the wire will connected to the meter. The meter which can convert DC current to AC current. DC means direct current. What is the difference between DC and AC? Direct current, direction of the current is one. Okay, only one direction. AC current, the direction of the current is reversible, which is the full term is alternating current. Okay, AC means alternating current, DC means direct current. The meter can convert DC current from the wire, okay, to your household circuit. DC to AC, the meter can convert. Now, from the meter, the wires will connected to the distribution box. Distribution box means in your home where the fuses, different MCBs are connected. Okay, say this is one MCB, this is another MCB, this is another MCB. Different MCBs are connected. This live wire, neutral wire will connect to the circuit, and then it will connect to different switch boards. Suppose this is one switch board, this is another. So plug of the switch board. Okay, three plugs are here of different three switch boards. There will be three holes. Here. Now, live wire is connected to one terminal. Here also, here also, and the neutral wire also connected to one terminal, like this. Now see, both the ends are connected to the same source. It means that your connection is parallel. This is a parallel circuit. Now this hole, it is considered as the earthing. Earthing means one wire with green insulation. Okay, another one wire, it is connected to the earthing. Earthing. Now this wire will ground inside the soil. This is called earthing. Why this wire is required? Suppose in case due to the short circuit, okay, short circuit means suppose the connection is loose, or the wires, the insulation of the wire is wears out. In that case, the excessive amount of current will passes through the ground wire, it will enter inside the soil. This is the main reason why the earthing wire is connected in every switch board. What is the function of fuse? The fuse only allow to enter the limited amount of current to your circuit, not the excessive amount of current. If for any reason excessive amount of current wants to enter your circuit, in that case the fuse wire breaks itself and your whole connections will shut down. Clear? Now this is the household circuit. How you can prepare your household circuit? First, live wire, neutral wire connected to the fuse, then meter, then distribution box, then the wires parallelly connected to each and every switch boards, each and every plugs. Okay? So this is the household circuit. Clear? Now, this is the basic. These topics are the basics of this chapter, magnetism. So when you go through the NCERT book, you will learn more about this chapter. And please always read the NCERT book. See the questions, in-text questions. Okay, then you will able to solve the questions here. Say one question is like you are using an AC, which is a rating of 17 ampere. 17 ampere current is required. Okay. Suppose your MCB or fuse is of 15 ampere. Now this 15 ampere fuse in the 15 ampere fuse, you cannot run the 17 ampere AC. It will cause overloading. So in that case, another 5 ampere or 2 ampere fuse is required. In that case only you can run that AC. Clear? So when you read the MCQ, you will get better knowledge about this chapter. So that's it for today. So in the next video we will again discuss about the whole chapter carbon and its compounds. Okay? In the next chapter, next video we will discuss about the chapter carbon and its compound. So thank you.